Hi again. In Module 1, one of the topics that we covered and told you that it has a huge importance and influence on engineering calculations and engineering skills of dealing with different problems was the concept of contour volume analysis. As you guys have noticed so far, for many problems we really don't know all the details within the problem. But we can always select the contour volume and isolate our system from the outside world, very much like free body diagrams that we have done in statics courses in undergraduate studies, and then think about what will happen in terms of outside world influencing things around our contour volume and how that will reflect into a balance between fluxes of things such as mass, momentum, and energy coming in and out of our system. We notice that to really be rational and logical about this, we need to base our mathematical formulations on something that is reasonable and is consistently true no matter what geometry or what conditions we choose as our contour volume. Because you can easily see that you can choose a contour volume that may be different from your other colleague or your other friend. And it's important to see that all these different contour volumes at the end will give you a same final result, because physical laws do not know anything about the contour volume we have chosen. In order to do that, we borrowed the idea of Leibniz rule in vector calculus. And if you remember, Leibniz rule tells us that for a 3D geometry, such as a closed volume that I call an arbitrary volume AV, I have an arbitrary surface AS, and this arbitrary surface may be stationary and fixed or may be moving with a certain velocity V sub AS. If there is a field property where small f is that field property per unit mass. For example, if the field property is the mass of particles, mass per unit mass would be 1. If it's linear momentum per unit mass would be velocity. So F is really the intrinsic representation of that field property. If we have a field property, when we integrate it over the entire volume of an arbitrary volume, that would be the net amount of that property that we have inside this arbitrary volume. Because when you multiply it to density, it becomes per unit volume. When you integrate it over the entire volume, that will give you the net amount of that property that you have inside this blob. The net rate of change of that identity with time is something of interest that again and again shows up in many different physical laws, because we are usually writing physical laws for a specific volume or body of fluid or body of objects, and we follow it in a Lagrangian manner, which will be this type of derivative. Now, to really understand what happens to this, we use Leibniz rule, and Leibniz rule tells us that there are two sources of change. That property can change within the volume, so we can take the rate of change of that property inside the volume for each element and calculate it and then integrate it over the entire volume. In other words, we bring d over dt inside and it becomes a partial derivative. But at the same time, the surface of this object may start moving in the domain. And with the motion of the surface, with a certain velocity that is described by the velocity of the arbitrary surface, we sweep things in or we throw things out with a certain rate that would give us a net change to the overall amount of that property that we have inside our arbitrary volume. So we need to really bookkeep both things together. We use this idea to actually apply it to a contour volume. Contour volume that is entirely up to your choice. You choose the contour volume based on the problem that you have, and it's basically your choice. Similar thing can be said about the contour surface and conditions on the contour surface. Whether the contour surface is stationary or whether it has a velocity that, for example, we describe as V sub c, is again up to you. Whenever you choose a contour volume at a given time t, there is a certain amount or blob of material inside that we call the material volume filling our contour volume at time t. That material volume, it has exactly the same shape similar to our contour volume at time t. But an epsilon of time before that or an epsilon of time after that, it may have a different shape, because this material volume may blow in or out of our contour volume. But at time t is entirely filling our contour volume. So the shape of the material volume and the shape of its material surface is exactly equivalent to the contour volume and contour surface. However, the main important difference between them is the fact that the velocity of the contour volume is what we prescribe and what we decide, but the velocity of the material surface, which we show as V, is indeed nothing other than the velocity field of the fluid elements. So this is set by the flow. We cannot really control this. Fluid elements enter and exit based on the flow field. However, the choice of the contour volume and the choice of the contour surface description of velocity will allow us to have freedom here. Now, if we use Leibniz rule and apply it on a material volume at time t, we can write down exactly similar form. So d over dt of things such as rho f dv integrated over the entire material volume at time t becomes equal to, so indeed I change anything that was arbitrary volume with material volume. So it will be material volume at time t, partial comes inside the integral, rho f dv, and I would have again material surface at time t, flux at which the field property is coming inside or outside my material volume, which would be the velocity of the material volume at its surface, which is the V, dotted to n, integrated over the entire area of material surface. Now, this was just Leibniz rule applied on the material volume that at time t has filled my contour volume. These two identities, the fact that material volume is equivalent to contour volume and material surface is equivalent to contour surface, will help us to actually write something simplified and maybe also meaningful and useful for ourselves. Let's do that together. So again, the left-hand side, and I'm going to continue it here, the left-hand side would be something similar, d over dt of the integral of everything inside material volume at time t, rho f dv, which, by the way, is the important parameter in most physical problems that we are looking for. The rate of change of certain property of a material volume when integrated over the entire volume as we move with it, the Lagrangian concept that we discussed before. This can be written equal to the two terms that we have here, this term and this term. But remember, we can switch the integral over material volume to the contour volume because these two are equivalent at time t, and to switch the material surface to contour surface because of the equivalence that we discussed. So this becomes integral of d over dt comes inside, and then you have rho f dv integrated over the entire contour volume at time t, plus the second term, which would be again rho f. But we need to be careful. The velocity used here is the velocity of the material surface, which is the velocity of the flow field. This is not the velocity of contour volume. So this should be indeed velocity of the flow field, which we use as v, dotted to n integrated over the entire area on the contour surface. If you look at your notes, this is nothing other than what we described as form B of Reynolds transport theorem. So applying Leibniz rule on a material volume gives us the Reynolds transport theorem in form B. Now, with a little bit of trick, you can also use Leibniz rule and apply Leibniz rule on the contour volume. When you do that, you will find a new way to describe this first term as a combination of some other terms, and then you can get form A. And if you remember, so again, here, I'm going to continue on this corner, and I'm going to write down that we apply Leibniz rule to the contour volume at time t. And when we simplify it, after simplification, we get the following. That again, the important parameter that we are looking after, d over dt of the entire property integrated over the entire volume of the material volume is equal to Now, here what we can do is we can keep the d over dt outside the integral. And here we have rho f integrated over the entire volume of the contour volume plus the other term, which would be rho f. And the velocity would be the relative velocity, which is v minus v sub c dotted to n dA. And this integral is done over the entire contour surface. And if you remember, this was indeed what, again, we described in the class as form A of Reynolds transport theorem. Dealing with different problems, you may be tempted to use either form A and form B. Your solution should give you exactly the same result no matter which form you use. These are the same ideas just described in two different ways. I personally feel form A is more helpful when you deal with a problem from scratch. So whenever I want to start a problem and think about solving it, I first apply form A. If I see things are becoming complex and may see a point that form B may be actually slightly easier or more intuitive, I switch to form B. But I usually have seen most problems, almost around 90+% of problems I have seen, to be easier, to be easier and more intuitive when you deal with them using form A. The idea, again, comes from the fact that we need to really describe something that is of importance from a Lagrangian description to the Eulerian description. The Lagrangian description is mostly useful for physical laws. What we need to do is to write it down in a certain way that can be applied to our contour volume of choice. A question that always comes is, what is really this value of f for different properties? And for that, I really suggest you to look at the handout by Ayn Sonin that is posted on the website. But just as a reminder, for example, is the intrinsic property per unit mass. So f for mass would become mass over mass, which becomes 1. F for linear momentum, for example, becomes mass times velocity divided by mass, which becomes velocity vector. For angular momentum, for example, it becomes mass times angular momentum, which is r cross v. So when you take that per mass, it becomes r cross v. You can look at the expression for f for example, energy, and other examples that have been described in detail in Sonin's handout. In the next video, we try to use this idea and solve a simple problem, and to show you that this concept is powerful enough that you can approach different complex problems using this approach and find really good, accurate engineering solutions to those problems.